Hi everyone, this is Zhengyu Liu from Johns Hopkins University. I'm happy to present our work, Undefined Oriented Programming, Detecting Chain Gadgets for Platform Vulnerability in Node.js Template Engines. So platform is a relatively new vulnerability in JavaScript. Considering a web application that's trying to update the user information on the server side, we'll likely come across this line of code in the merge function, which tries to recursively merge the content provided by the client to the user info object. However, there's a special property in JavaScript object named double underscore prototype underscore, which can be seen as a pointer points to its prototype object. For the user info object, it points to the root prototype, which is inherited by all the JavaScript object by default. That's how JavaScript implements inheritance. By leveraging this special property, the attacker can craft the payload to modify the root prototype at the runtime, and this will become a severe problem. Since platform vulnerability has come out in 2018, a lot of work have done to detect its vulnerable code pattern. However, platform is not the end. To escalate the consequence from polluting the root prototype to cross-site scripting or remote code execution, we also need to leverage the gadgets. So what is the platform gadget? Here is a simplified example to show the concept. For the property lookup on line 3, highlighted in green, when the current block object does not have the key named n, it will look up through its prototype chain all the way to the root prototype. If none of them have the key named n, it will return an undefined value. This process is known as an undefined property lookup. However, with the existence of platform vulnerability, the attacker injected value will be returned back from the lookup. As program get proceed, the payload would flow to the sink like function constructor through the data flow, and the injected value will get executed. This is what we call direct platform gadgets, as it directly flows from an undefined property lookup to the sink. However, we don't always get what we expect. There is an if condition on line 4, highlighted in orange, which will block the attacker's payload from reaching the sink. That said, under normal program execution, the variable type would never equals to the string s, and actually this branch is a dead code. So the direct edge is no longer working in this case. It's also where the previous work failed, as they only support detecting this kind of direct platform gadgets. However, from an attacker's perspective, it challenges us to carefully reconsidering what we have control of right now. Then the question would become that, can we leverage another gadget to alter the control flow of this one? And the answer is yes. There is another interesting undefined property lookup in the code, which is marked as green. By tracing down its data flow, its value may finally flow to the if expression that hindered our previous gadget one. By carefully crafting the payload that follows this data flow, the attacker can control the value of a variable type used in the if expression, enabling us to change the control flow of gadget one. So this is what we call the chained platform gadgets, that said we exploit one gadget to affect the control or data flow of another gadget and lead the payload flows to the sink. And actually, the concept of gadget chaining has been used in the exploitation of other languages and vulnerabilities. In the area of binary, people have posed return-oriented programming. In short, rope chain when attacker can overwrite the return address on the stack. The gadgets are chained through the return instruction. Similarly, in languages like Java, PHP, and Python, property-oriented programming has been developed for the object injection or visualization vulnerabilities. It has been used to construct complex object structures that lead the program to perform malicious behavior during the object installation process. The gadgets are chained through conflicting property or method names across different classes. Therefore, in JavaScript, we coined the term undefined-oriented programming for the propulsion vulnerability. The gadgets are led by different undefined property lookups and chained through its effect on the control or data flow during the execution. So our main research question fell in two parts. Firstly, we tried to answer the question that how can propulsion gadgets be chained together and how to categorize or summarize the relationship of those chain gadgets. And the second question is that how to automatically find chain gadgets in the wild. To answer the first question, we proposed the first taxonomy for the chain propulsion gadgets. To better categorize chain gadgets that appear differently, we have proposed two distinct criteria, one based on gadget payload, the other one based on the gadget dependency. Based on the gadget payload, the gadgets can be horizontally chained or vertically chained. In our motivating example, the gadgets are horizontally chained because they require the pollution of two properties in the root part type, triggering two distinct gadgets in the existing code. Based on the gadget dependency, the gadgets can be data flow dependent gadgets or control flow dependent gadgets. Regarding our motivating example, the gadgets are control flow dependent, as the gadget 2 affect the control flow of gadget 1 and help it derive the payload to the sink. We also featured two interesting examples of vertical chain, or it's called like self-chain gadgets, and the data flow dependent gadgets. Here's an example of vertically chain, or we call self-chain gadgets. The code shown in the list 4 is a parse function which tries to walk through the ASD tree recursively. Well, there's an undefined property lookup on the line 4, highlighted in green. With the existence of propulsion vulnerability, the attacker can pollute the property block in the root part type, and the program will perform the walk ASD function on the attacker injected values. However, after we pollute the root part type, the line 4 will never become undefined again and will get into true branch all the time. To stop the infinite recursive call, we need to break it out. Therefore, another nested layer in the exploit object with the name block is necessary. We call this gadget self-chained because the payload will trigger the same gadget multiple times with different values, and the payload has nested layer with the same property name. Besides, regarding the data flow dependent gadget, it's very useful and commonly seen in the real-world exploitation. But pollution will usually break the functionality and prevent us from exploiting the gadgets. This example would be a common case on why the propulsion will break the functionality and show how we patch it. There's an undefined property lookup in the stringify substitution function, where the following loop will look up to the root part type and loop out the attacker injected key. And then the looped key will float to the sink, which looks great. However, before the stringify substitution function get called, there's another foreign loop in its caller function. And when the injected key has been looped out and used in the loop body, it will raise an error on the line 5 as the lookup will retrieve the corresponding value from the root part tab and with it its name property. However, our injected value is a string, and it does not have the property named name. And this will result in undefined value passed to the ESC function. And the ES function will raise an error as it expects the argument has the type of string. Therefore, we need to put another property name in the prototype to patch the data flow. We call it data flow dependent gadgets because the pollution of the first gadget will alter the original data flow by introducing an undefined value, which will accidentally raise the error. To correct this, we must adjust the data flow using another additional gadget. Next, we come to our second research question: how to automatically find the string gadgets in the well. To resolve the challenge, we present the undefined oriented programming framework, in short, OOP framework. The high-level idea behind is that we concurrently explore the program state by setting the undefined properties as symbols and leave their value flow to the sink. So our system operates in three phases. In phase A, the OOP framework generates the minimal test unit for the code execution, which includes three components: a target library, a test case with normal input, and a set of undefined properties under testing. Specifically, given the target library and the test case, we perform an approximated call graph analyze to select out a list of export APIs which will reach the sink potentially. With the select out test case, we random our instrument Node.js runtime to collect a list of undefined property lookups. With identified undefined properties, the scheduler would organize the test units and start the execution engine. In phase B, the system concurrently executes the test program by exploring different paths that the propulsion inputs can lead to. Throughout this process, OOP framework also collects the newly discovered undefined properties. Finally, the process A and B will be repeated to test these newly added undefined properties. Let's use the motivating example to showcase how the execution engine works. Let's start with looking at the second gadget. Given the undefined property under testing, we will first plot it with a concolic value, which contains a concrete field and a symbolic field. Then we'll model all the operations that the concolic value encountered and update the payloads accordingly. For example, we immediately observe a property lookup on our injected value. It indicates that the settings property is an object which has a key named view options. Therefore, we will initialize it lazily. Then we found the prefix properties has been looked up on our concolic variable. Therefore, we'll lazily initialize another nested layer named prefix. Next, we encounter a for-in operation on our concolic variable. The for-in operation requires careful handling since the key names and values used the loop are both unknown. To capture the constraints associated with both the key and the value, we introduce a symbolic key to the object, which itself is a concolic value with a type of string, and also a concolic value for its corresponding value. Within the for-in loop, we identify the constraint of our injected value. Whenever we come across the condition where the concolic variable has been used in the expression, it indicates that we have a chance to use the injected value to negate the current result and activate a new control flow path. Therefore, we will solve the constraint and get the concrete value. With the if condition satisfied, we note that the injected key has been used in the compile scope function, which aligns with the if expression that initially prevents the get one. After solving the constraint, we now get the payload for helping the desired control flow for the first gadget. By getting the undefined property n involved and test them together, finally, we can observe that the concolic value has flowed to the sink and the system will learn about the gadgets. Here's our evaluation. We have tested the OOP framework to a collection of Node.js template engines from a GitHub repo and uncovered 26 zero-day gadgets, and 30 of them are chain. And some of them are really popular template engines which have more than 1 million downloads in the past year. We have responsibly disclosed all the derived gadgets to the developer, and 7 of them have already been fixed in their latest version. We also evaluate the false negative and false positive R2 using 2 benchmarks. The first one is curated by us, which contains all the known pollution gadgets in the template engines. The second one is a GitHub repo, which contains a collection of template engines. We have compared with the 2 pro by the previous work named Silent Spring, and also its variant, which uses the undefined property found by R2. Together with R2, and we test on the 3 artifacts on both benchmarks. It shows that R2 significantly covered their results. And notably, Whoop framework doesn't have any false positive. In terms of performance overhead, the total analyzed time consists of 3 parts. The static analyze part in phase A, the search time for different undefined property combinations in phase B, and the final exploit generation time for constructing the correct payloads for the exploitable gadgets. Our observation is that static analyze is relatively stable across the detection of different gadgets, and also small compared with concurrent execution. The gadget search time dominates the entire analyze time in most cases. The reason is that Whoop framework tries different combinations of undefined properties in the concurrent execution, which is a relatively heavyweight process compared with a static analyze. And lastly, the exploit generation time is mostly small compared with the static analyze and gadget search, but it could be large in some cases. Specifically, in one case, the number of branching statements leading to the sink is large along the exploitable control flow path. Therefore, the exploit generation times is much longer. Here it shows the end-to-end analyze time of Whoop framework in detecting and exploiting gadget chains with regard to the test number of undefined properties in a template engine. The figure tells us that the number of undefined property increases. Analyze time also increases roughly linearly, which indicates that R2 is scalable to a large template engines. Finally, we answered the question on Whoop framework's capability in discovering new undefined properties with the increased code coverage and more unique control flow. More specifically, we choose 3 template engines, namely EGS, PUG, and JADE, and show their code coverage, number of unique control flow passes, and newly discovered undefined properties over time. We have 3 observations. Firstly, Whoop framework helps to explore the target program to find new code for the gadget exploitation. The horizontal lines in each subfigure are the code coverages without any pollution inputs. Whoop framework does help the target program to reach previously unseen code for the pollution chain exploitation. Second, the code coverage tends to stay stable over time after initial increase, but the number of unique paths keep increasing. The reason is that Whoop framework is exploring code that has been analyzed before. However, different combination of code will lead to different unique control flow passes. And lastly, Whoop framework keeps discovering new undefined properties. The bottom graphs of the figure shows that the total number of undefined properties keep increasing. And finally, in this paper, I'm happy to introduce a new member, Undefined-Oriented Programming, or in short, Whoop, to the house of gadget chaining in the exploitation world. Now, the tool is open source in the GitHub, so please take a look if you are interested in it. Thank you for listening.